has Chalkworth, I think.
Ones?
Yeah, I think so. It's like 1933 or something like this. It's horrible.
That sound like that old.
That's right, exactly. I did. Okay, I don't know what I'm talking about. Okay, so consider the following linear system once again, where A is given by alpha, beta, minus beta, and of course, alpha, beta is not equal to. It's very nice chalk color actually. It's a nice contrast. I don't know, I like it. Okay, anyway. Okay, so did I start with this example last class or did I finish this example?
You didn't do this.
I've not done this. Okay, good. Okay, so as usual, as I said, our usual theorem says that the solutions to such a system of equations depends on finding the eigenvalues and eigenvectors of this. Okay, so let's do that. Eigenvalues, then. So I'll save you some time. I'll write down the characteristic equation. Assuming that you can do it for simple 2 by 2. So lambda squared minus 2 alpha lambda plus alpha squared plus beta squared is equal to. So that's the characteristic equation for the eigenvalues of this. And if you solve this, you see that the solutions, you get 2 eigenvalues. So it's a simple quadratic equation. You can use quadratic formula. So the first eigenvalue is lambda 1 is equal to alpha plus I. And what is the other eigenvalue then? The conjugate. So the complex eigenvalues case is very nice because you can always find out just one of the eigenvalues and reverse it.
Are you recording?
I am.
Yeah. I was going to say, last time I was not that good. I mean, like, you have to bring it closer a little bit.
Now it's in the third one. Oh, it's right one. They're not that good.
This is very bad.
What do you think I have, like, unlimited budget production?
So far that you have to, like, kind of squint.
No, but if you actually make it big screen,
Yeah,
it comes, you did. Did you find the same thing?
No, I don't know.
No, I know, I moved it closer. That's why I put this line here, because the camera will cut off here. I know not. So see if it's better to you. It's very experimental. I have no mic, I have no lights, I have no quality to this. Yeah, I don't know. Anyway. Okay, so these are the eigenvalues of the matrix. And of course we need the eigenvectors. And the eigenvectors you can confirm are just by solving the following equation. So you get alpha minus alpha plus I beta times x plus beta y. So as you can imagine, any time you have an eigenvalue problem, finding the eigenvectors always involves finding one equation with two. Here is the x and the y. So we have to solve it as usual experimentally. So what is one possible solution to this? Of course it's just xy is equal to 1. So that's one possible eigenvector. And if you know one eigenvector, then you know the other one because it's just the complex conjugate. You erase my friend's epic question. No. I will learn how to do this at one. Okay. So therefore, one possible solution, so x of t, is equal to e to the eigenvalue, which in this case I'm taking the first one, so alpha plus I beta. times t multiplied by the eigenvector, 1r. So that's our, remember, our fundamental theorem. So the whole thing of solving linear systems equation is finding the eigenvalues and eigenvectors. And the minute you have that, you have the solution. Okay? But as I said, we would like to write this in the real components, not just the complex form. So let's see how we can do this. Well, recall that this is just e to the alpha t times e to the I beta t. If I expand out that. So this can be written therefore as e to the alpha t. Cosine beta minus sine beta plus I e to the alpha t. This should be sine beta t cosine beta. Just by breaking it up and using Euler's equation. And if you remember from last time, we were able to write this as a sum of real solutions and complex solutions, if you remember. So this can be written as x, I use this notation if I recall, x sub RET for x real, if I remember, yes? Asta's on, she's on board, she knows what I mean. Plus I times x imaginary. So you can decompose this solution as a component of real solutions plus imaginary solutions. So in general, what do you have? We can write that x of t, the general solution, is a constant, so call that constant c1, or alpha, but I've already used alpha and beta here, so I'll use c1 instead. c1 e to the alpha t, matrix solution, cosine beta t, minus sine beta t, plus c2, and I'm running out of room, but I'll just write it. E to the alpha t, sine beta t, cosine beta t. So that's the most general solution. It's in real, in terms of real components. So this is what I kind of did last time, but this is another example. So what does this solution geometrically mean? Every time we've done one of these cases, then we've analyzed geometrically what the solutions mean. In this case, what do the solutions look like? Can anybody guess? So the cosine and sine is a big hint here. So what does a wave look like if it's in x and y components? He said it's a circle shape. Very good. But what type of circle?
Circular.
So if it's like, no, I don't want to say. No, I've switched to not making fun of astronomy. After their silliness with these planets they discovered. But that's another story. Okay, so let me ask you this question. If the e to the alpha t term in front of those matrices was not there, then, as you guys said, the solutions would just wind periodically around, or I guess, for lack of a better word, around circles centered at the origin. As you can see, it's just cosine and sine function. But the point is we do have the e to the alpha t term. So how do they affect those solutions? So, but the e to the alpha t terms, what do you think they do? They contract them. to contract the spirals in some sense. Because you have circular solutions, but then you have this exponential function which is like damping that circular behavior. So it's causing them to shrink and grow, the sizes of the circle. So something like this. So this is the xy plane. You have this, but then you have technically the exponential function is a growth function. So it's changing the sizes of these continuous. So you have something like that. All around the edge. So if these exponential functions are not there, you would just have one circle, but the fact that they're there in time, you have concentric circles around the edge. And as you can confirm, if alpha is less than 0, then these solutions spiral into the origin, so in 2, 0, 0. If alpha is greater than 0, it's the other spiral away. So very fascinating. I think you will know. So, any questions about this? So we've done the cases of real eigenvalues and distinct. We've done the cases of complex eigenvalues. So which is the case I've left out? That's the second case. I'll get to that later.
The same.
Repeated eigenvalues. Very good. So let's see what happens. This looks very professional, this blue top, I must say. It's very nice, I like it. I'm saying it, I've never seen it like this. I wonder what happens if I use red or green. Okay. So the final case is the repeated eigenvalue. So a simple case of repeated eigenvalues, you can just guess, is when A is equal to lambda 0, 0. Obviously the eigenvalues, this is a diagonal matrix, so the eigenvalues are just lambda. So that's the simplest case you can have. Here, the eigenvalues are just lambda. So then, what are the eigenvectors of this? Any others? Think about it. Look at the matrix. What are the eigenvectors of this matrix? It's two-dimensional. So my claim is in fact that any non-zero vector is an eigenvector of this. Because you can show that A times B will always equal to alpha, lambda B, for any B, because lambda is equal. So it's the same idea. The solution, therefore, the solution is still x of t, alpha e to the lambda t times t. That never changes. It's always e to the eigenvalue times the eigenvalue. But what about a slightly more complicated case? What about let's take A to be a slight modification of that. So let me give it lambda 1, 0, 1. So I put a 1 there instead of the 0. The eigenvalues, as you can confirm, are still the same. Where lambda 1 is equal to lambda, which is equal to lambda 2. So eigenvalues have not changed. But the eigenvectors not changed. But there's just one linearly independent eigenvector, which in this case, as Gates already said, is just 1, 0. So then therefore we only have one solution, which is a problem. Because it's a 2x2 system, we should have two solutions. Yes?
Are they the same because they're similar matrices? Is that one?
This matrix and that matrix?
Yeah, is that why they have the same eigenvalue?
No, this is a different case.
Oh,
It's a different question.
but you said they have the same eigenvalue.
I meant, yes, but as an example, not specific to this problem.
Okay.
You see what I'm saying? I didn't mean to, like, pretend I didn't do that example. What were the eigenvalues of this?
Oh, okay.
I mean, they're very separate questions. Yeah. So as I said, we have one eigenvalue and one eigenvector, but we need two solutions. So how can we do it? So one solution is x1 of t given by alpha e to the lambda t times 1. What about other solutions? So if I know one solution, how can I use that solution to generate other solutions? Well, if I look at this matrix, x prime is equal to ax once again. Let me write it out in component form, as I've been done a few times. So given that matrix A, and given that x is generically just xy, let me write it out in equation form. Okay? So I'll get that this is the same as x prime is equal to lambda x plus y, and y prime is equal to lambda. But then, you see, in some sense, the equations have decoupled. This is no longer a system of equations, because the second equation doesn't depend on x at all. So I can solve it independently of the first. So let me do that. So much of my time in this class is spent in erasing this code. I don't. Anyway. So, if, of course, y does not equal to 0, what is the solution of y prime is equal to lambda y? What is the solution? Simple first order, test 1, question 1 type question. If y prime is equal to a constant times y, what is y is equal to? Yeah. Everybody's forgotten? No. You cannot do this. Remember, it's a simple separable equation. You can solve both sides. You all did it on test 1. I know you did it, because you all got 5 out of 5. How is this now you've forgotten? This is embarrassing. You should not forget this. Okay, anyway. So y of t is simply equal to some other constant, let's say beta is equal to e to the lambda. Please at least know this if you don't know anything else. Okay, so we have another solution. So I will substitute this back into my x prime. The x prime is lambda x plus 1. So therefore I get x prime is equal to lambda x plus y, but we norm y is just b to the e to the lambda. So lambda x plus b to the e lambda. Which of course means that x prime minus lambda x is equal to b e to the lambda t. Dare I ask you to solve this first order equation? What is the integrating factor?
Minus lambda d dt.
Yes. Remember, this is y prime plus p to the ty is equal to g to the. And we solve it by using integrating factor. Well, so the integrating factor is just mu of t is equal to h, the exponent, minus lambda. I'm just reviewing this, but you know how to solve these kinds of equations. I hope you know. Okay, so that's the integrating factor, then we know how to solve this first order equation. So in fact we get, just multiply both sides of the over the 8 by this integrating factor. Just by multiplying both sides of this. And then this is just trivial to solve because I can just integrate both sides. So x of t in this case is equal to exponent lambda t times beta t plus mu exponent I use the same notation for my constant, so maybe I should use something like this. Let me use gamma instead of it. Because I call the integrating factor mu, I don't want to use it. So therefore, we've solved the system. We have an x of t solution, and we have a y of t solution. So therefore, x of t is equal to exponent lambda t beta t plus mu exponent lambda t, and my y of t solution is just beta exponent. Ah, yes, sorry. Thank you. Okay, but I gave you the question in matrix form. So the polite thing to do is to return it to me in matrix form. No? That's bad. But it's very easy then to write this in matrix form because you know the basis bit. So then xy, which is the solution, is simply given by gamma exponent lambda t times 1, 0 plus t times 1 beta exponent. So that's the same. You don't have to do this extra step. If you're okay with that, it's okay. As long as you solve this. But note that, do you remember when we did the repeated eigenvalues cases for the second order differential equations? It was the most boring case. Because all we did was we multiplied the first solution by t. And you see that's what happened here. We have our solution. All we did to get the second one, essentially what came out was a multiplication by t. So that's the boring repeated eigenvalues.
Sir,
Yes?
what is the first vector?
It's 1, 0. It should be 1, 0, not... Yeah, I was going to say that too. Okay. Alright, so those are the three cases. Distinct eigenvalues, complex eigenvalues, and the boring repeated eigenvalues. And of course, as you've seen so far, the behavior of the solutions completely depends on the signs of the eigenvalue. But in this case, if you have one eigenvalue and it's repeated, it turns out, as you'll see later, the behavior behave the solutions also depends on the sign of the eigenvalue. You can, but it's a little bit more complicated, and we'll get to, I'm saving the general case for the nonlinear systems, which we'll get to hopefully next week. Okay. So I'm debating. So tell me something. How many people here have taken linear algebra? Okay. Now the question is what they did in linear algebra. Did you do transformations of coordinates?
Yes.
So a matrix of transformations like T is equal to A, B, C, D. So I know you've done it. But does everybody know what I'm talking about? Something like this. Okay. Okay. All right. So let me make this point. I will just erase this because I'm too lazy to walk. So I got this question. I forgot who asked me this question in email, but I said I'll answer it today and I'll answer it today. If you actually look, I've only dealt with 3 possible cases of linear systems with very specific matrices. If you actually go back and look. So one of the matrices was like this. That was our first case. Another matrix was when I had the complex eigenvalues, which was this case. And then the final case is what we just did. So we've only done these 3 cases. And of course, in this situation, you can have that lambda is equal to mu, which just gives you a simple case of the group. So you could ask, why have I cherry-picked these 3 matrices? And it turns out that, in fact, you can write any linear 2x2 system in one of these matrices. So these are what they call canonical matrices. Some actually call it the Jordan canonical form. So any linear 2x2 matrix or linear 2x2 system, you can write into one of these cases. And the point is, why does that matter? It doesn't, really. Because it doesn't matter what matrix I give you. As long as you find the eigenvalues and eigenvectors, you have the solution. But in terms of the behaviors of these solutions, you know what the behaviors of these 3 matrices are because we've done them the last 3 classes. So any linear, you have an option then. So if you are given some linear system of equations and I ask you to solve it, you can just find the eigenvalues and eigenvectors and write down the solution. And you're done. You don't have to do anything. But the point is, if you want to know something more deep about the solutions, you know that you can transform them into one of these. So did you do this in linear algebra? Turn them into the Jordan canonical form? No? Okay. Let me briefly explain this. Let me because it's quite important. So my claim is that any 2x2 matrix in this form or in one of those forms is what we call canonical form. And given any linear system, so call it x prime is equal to ax, I can change coordinates / transform coordinates to convert A into canonical. It's very fascinating. fascinating actually. Okay. So how do I accomplish this? Well, let me consider the following linear transformation. So linear algebra people, how do I write down a linear transformation? Acting on a vector. What is a linear transformation? Technically it's just a matrix.
Yeah.
Right? It's an operator. So when you study higher order, I guess, or more sophisticated linear algebra, you'll see that linear transformation is just operators on these matrices. So let me consider, call that linear transformation T. Okay. And it's a mapping that goes from R to R. So it takes a R2 for a vector and gives you back the vector. The question is, what does this linear transformation look like? So take T operating on my vector x, y. Let me take it as the following. Ax plus by, Cx plus by. So this matrix T, when it acts on this vector xy, gives you another transformed vector, Ax plus by, Cx plus by. So as you can see then, T must have the form A, B, C. So take A, B, C, D times xy, you get this. So this is my transformation that operates on this 2 by, or 1 by 2 vector and gives you another vector. So that's the first thing. Now suppose that T, which is this matrix here, is invertible. That is, T has an inverse matrix, call it S, for lack of originality, call it S. So then, if S is the inverse of T, what does S product T give you?
1.
Identity of 1. So therefore, ST is equal to S, which is the identity. And I mean the identity matrix. So I is equal to 1 and 0. Okay. All right. Now, if I asked you to compute the inverse of this matrix, you can do it very easily. Assume you remember how to do this. You can show that S is equal to 1 over the determinant of T, which is just a number, D minus B minus T. So I'm assuming you know. You didn't know how to do. Look. No, I understood. So how can I check very easily that S is in fact the inverse of this matrix? Say it again. And how can I show that S is the inverse of this matrix? And what do I get there? So if you do that multiplication indeed, you'll get 1 0. Fine. So S, I'll just rewrite it here. So D minus B minus C A is equal to T inverse if what? What is the condition that the determinant of T cannot be equal to 0? Obviously. We have 1 over D determinant T, so if it's not equal to 0, then we're good. So that's the condition. So keep that in your, I guess, back of your mind. Okay. So now let's go back to my linear system, x prime is equal to A. And let me now consider a different version of the system. In other words, let me consider a transformation of the system. So let me consider now y prime is equal to T inverse A times T, X, or Y. Recognize what this is. What is this factor in the bracket? How does it come about from the original matrix A? What am I doing to A in here? Very good. I'm diagonalizing it. So there's some deep relationship between this system and this system that clearly depends on the diagonalization of A. So let's see how this works. In other words, if y of t is a solution of this new system, then x of t, my claim, if y of t is a solution of this new system, then x of t, which is given by, let's say, t times y of t, is a solution to the original system. Is a solution to x prime is equal to A x. So that's why we picked only those three cases. Because you can always diagonalize and use a linear transformation in this form to convert it to one of the canonical. But this is just for lack of a better term, security purposes, okay? To show you that the machinery behind this is well defined. But you never need to do this to actually solve a linear system. It's always as easy as finding the eigenvalues, and writing down the solution. So this is just to show you there's a big linear algebra machinery behind a dynamical system. So, I just wanted to make that. Okay. So now, any questions? Okay. So now let me actually go one more level of abstraction. Because linear systems are a bit boring, I think. But aside from the fact that they don't really exist, but that's quite different. I don't have a problem with this is being recorded, so I'll tell you in 10 minutes what it is. I mean, they're 40 light years away, and you have these artist depictions of what they look like. And every astronomer flocks to the closest TV station to associate themselves with this discovery somehow. I don't understand. Anyway, okay. So let me come to this following subtopic, which is called dynamical classification. So one of the things, actually one of the most important things in dynamical systems theory is not the behavior of solutions themselves, but the behavior of the long-term behavior of these solutions. So, in other words, well, I don't want to talk about diagrams, but in other words, if I give you some system of equations, can you just by looking at the system somehow, without actually solving it, can you see what the long-term behavior of this solution will look like? So in other words, if I let the system run for a very long time, what do the solutions tend to? Do they tend to some specific state? Do they have some weird behavior at that time? So that's the type of questions we really are interested in. So let's give some hints. And in fact, when we do nonlinear systems, understanding this is the most important thing, because you cannot solve the vast majority of nonlinear systems. So getting ideas of behaviors through these types of methods is very important. So in dynamical systems, which I'll just put here for sure, we are interested in long-term behavior of solutions. But note that even for a differential equation, all solutions depend on two things. First, they depend obviously on time. And on what other factor? Initial conditions. Very good. It is a big problem, actually, in physics, that a lot of physicists, especially those working in cosmology, do not understand this problem. That in nonlinear equations, the solutions to your system heavily depend on the initial conditions you set. As you saw with one of the bonus questions. Because it really depends on choosing initial conditions such that either the solution will completely blow up or will be well behaved. So it very much depends on the initial conditions you choose. So therefore, even in higher order systems, all your solutions depend on good initial conditions and obviously. But what I'm calling time is a bit fuzzy too. I mean, I don't necessarily maintain time, I just mean some independent labeling parameters. Anyway, so if I denote my initial condition, let's denote it by the matrix x0, for lack of a better term. And let me denote by phi for my Greek friends sub t of x0. Let me denote this function as the solution that satisfies the initial condition x0. So by phi sub t x0, I mean the solution to this dynamical system that satisfies the initial condition. That's what this notation is. Okay. So what I mean to say is that phi 0 at t is equal to 0 of x0 just gives you x0. That's what it is. And we denote by phi t x0, which I write shorthand as this. So just to show you that my solution phi depends both on time and initial condition, we shorthand this by writing it like that. And what we call this very specific form of solution, when we write it like this, we call it the flow of the differential equation. A very, very, very important concept, especially when it comes to nonlinear. And some people, they just write phi sub t, and what this means, they mean the time t map of the flow. So what am I saying here? Geometrically, what is special about this solution? What am I writing down? If you picture in your head, what does this mean? So, this solution has a mapping of all possible